Hi, this is Ms. Fitzmaurice, and this video is an explanation of free response problem number 6. That's on page 11 of your review packet. And this was also the 1992 problem on the AP free response section. In 1992, Bill Clinton was elected president. And after hundreds of years, the Pope finally pardoned Galileo Galilei for claiming that the Earth revolved around the Sun. Alright, so in this problem we have another circular motion problem. A ball attached to a string is moving around in a circle. We know that the string has a length of 0.8 meters. And in part A, we want to know the total energy of the ball using the floor as 0 potential energy, so our height is 0 right here. Okay, so to find the total energy of the ball, we might as well look at the point where we have the most information. At the top, we know the height, and we also know this ball is moving at 6 meters per second, so we'll be able to find the total energy. Okay, so all of my energy at this point is going to be equal to my kinetic energy plus my gravitational potential. There's no spring in this situation, so in this case it'll be 1/2 mv squared plus mgh. I know that the mass is 0.1 kilograms, so I can just go ahead and plug those numbers in. And my height, that's the only slightly tricky thing we have to think about. If the string has a length of 0.8 meters, that means the radius is 0.8 and the diameter of this circle is 1.6 meters. And we know from the diagram at its lowest point that it's 0.2 meters off the floor. Okay, so the total height is 1.8 meters. And that's what we're going to go ahead and plug in right here. So we can go ahead and we can calculate that. We know that 6 squared is 36 times 0.1 right here is 3.6 times 1/2 is 1.8 joules. Okay, plus 0.1 times 10 is 1 times 1.8 is 1.8, so we have 1.8 joules plus 1.8 joules for a total of 3.6 joules. And so this is our total energy no matter where we are in the circle. And actually it's going to continue to be our total energy even after this thing breaks from the string and hits the floor. Okay, so in part B, we want the speed of the ball as it hits point P at the bottom of the circle. Well, we know, let's call this A and this P. We know that all of the energy at point A has to equal all of the energy at point P. Okay, and so kinetic at A plus gravitational at A equals kinetic at P plus gravitational at P, and we can use this kinetic energy at point P, we can solve for it, and we can use it to find the speed at point P. Okay, so we know from before that at point A we have 3.6 joules of energy. Okay, and at point P, we have 1/2 mv squared plus mgh. We can go ahead and plug those numbers in. We have 1/2 times 0.1 v squared plus 0.1 times 10. At the bottom, we know that it is 0.2 meters above the ground, so that's our new h. And so we have 3.6 equals 1/2 times 0.1. So that's 0.5 times 0.1, or 0.05 v squared plus 0.2. Okay, we can subtract 0.2 from both sides. We end up with 3.4 equals 0.5 v squared. Divide both sides by 0.5. Oh, 0.05, excuse me. And we end up with 8.24 meters per second. Okay, so in part C, it wants us to determine the tension in the thread, A at the top of the circle and B at the bottom of the circle. Okay, so let's say this is A again, and this is point P. So at point A, the top, we can go ahead and draw a force body diagram. We have tension going down and FG going down. It's moving around in a circle, so we know that T plus FG is equal to mvt squared divided by r. Okay. At the bottom, we have, on the other hand, the tension going up and Fg going down, so we have T minus Fg equals mvt squared divided by r. Okay, and even though I didn't do it, you should always write out sigma Fy equals may. Okay, so we know, of course, that because it's going around in a circle, Ay is this. Okay, now we want to solve for tension. We want to solve for, tension. We know that in the first case, tension is going to be mvt squared divided by r minus mg. Okay, because we have to subtract Fg from both sides. And now we go ahead and we plug in numbers. So we have T equals 0.1. At the top, our speed was 6 squared divided by our radius, which was 0.8, minus 0.1 times 10. Okay, and when you plug that into a calculator, you should end up with T is equal to 3.5 newtons. Okay, so here is your tension. For the bottom, again, now we add Fg to both sides, so we get T equals mvt squared over r, and remember this is the velocity at the bottom, plus mg. And so we end up with T is equal to 0.1. Vt squared was 68, and R is 0.8, okay, plus 0.1 times 10. So we have, when you put it into your calculator, 9.5 newtons. Okay, so you have much more tension at the bottom than you do at the top, and that makes sense because at the bottom you have a bigger speed, so Vt squared over r is going to be a bigger number to begin with, and then you're sort of fighting the gravity force, whereas at the top the gravity force is working with the tension. Alright, part D says the ball only reaches the top of the circle once before the thread breaks when the ball is at the lowest point of the circle. In part D, they want you to determine the horizontal distance that it travels before hitting the floor. Okay, so what's happening is it goes around the whole circle. When it gets back down to the lowest point, the thread's going to break, and the ball will initially have a velocity, the same velocity it had, but it will fall down to the ground, and what they're asking you to find is how far along the ground did it get. Okay, so this is a 2D kinematics problem. You have to set up your XY chart. Okay, so we know that x naught x is equal to 0. Xx is what we want to find. We know that v naught x is the speed the instant it breaks. And so if we look back, that is 8.24 meters per second. So we have v naught x is 8.24. Vx will be the same thing because, as you know, ax is equal to 0. Now in the y direction we have xoy, xy, voy, vy, and ay. Okay, ay we can assume is negative 10. Voy, this thing at the bottom, at the instant the string breaks, is just moving from side to side, so voy should be 0. We don't know what vy is, but we probably don't care. The final height of the ball is 0, and we know that the initial height is 0.2 meters. Okay, so we can go ahead and we can use our y information to solve for time. Okay, so we do xy equals xoy plus voyt plus 1/2 ayt squared. Okay, we know that these two things go away. Actually, xy is the one that is 0, not xoy. Okay, and so we have 0 equals 0.2 plus 1/2 times negative 10, so that's negative 5 t squared. Okay, we can solve for t. We can bring this to the other side, so we have 5t squared equals 0.2. We divide both sides by 5, and we have t squared is equal to 0.04, meaning that our time is equal to 0.2 seconds. Now we take that time and we fill it into our x information. So in the x direction, we're solving for xx. Xx equals xox plus voxt plus 1/2 axt squared. Of course, we know that ax is 0 and xox is also 0, so we have xx, that's what we're trying to find, is equal to vox, which is 8.24, times t, which is 0.2, and we get a distance of 1.65 meters. Alright, in terms of the point breakdown, for getting part A all the way correct, you get 1 point. For part B, if you used conservation of energy, any indication of conservation of energy gets you 1 point. Solving correctly gets you a 2nd point. Part C, Okay, for each force body diagram, you get 1 point if it is totally correct. You get 1 point just for mentioning Newton's second law at all, so sigma Fy equals may, regardless of what the forces are. You get 1 point if you correctly followed your force body diagram for each, and then 1 point for both correct answers. So that's 1, 2, 3, 4, 5, 6 points total for part C. For part D, 1 point for using the first equation in y to find time, 1 point for using the first equation in x, and 1 point for the correct answer.